We're going to talk about our mesh types. We have quads, triangles, Cartesian, and blank. And then we're going to talk about the parameters that go along with these different cell types, but it's also the arcs. We talked about that yesterday. Zach talked about when you do quads, you're really like pushing stuff to the outside, not really keeping them on the inside. So it's a combination of region and arc parameters that go in to make the mesh. Oh, and then we'll talk about what happens when you have different regions next to each other. How do we transition between them? Our motivation here, why do we separate the workflow into a conceptual mesh, which you can edit, and a automated computational mesh, which you cannot edit? And this turns out to be a really, really good thing to do. It has some downsides. One of the downsides is you're looking at your computed mesh and you think, I'd like to just change that one cell. And in version 6, you might be quite accustomed to doing that. But if you think about what would actually happen if you did that, is you started making hand edits, then all of a sudden that 100 megabyte data set, which is that enormous mesh, now we have to save the whole thing, every step, every backup step, because we don't know what you edited or what you didn't. So we decided you can only edit the computational mesh, and there's enormous performance and backup gains out of that. Okay, but this new approach, when you can accept that, what we get is something that's repeatable, flexible, light, and obedient. So I mentioned yesterday that Stan coined that term. It's an awesome way to describe it because it encapsulates everything I feel about the old one, which is disobedient. Which is you're trying to achieve something and different break lines would fight and you wouldn't get what you wanted. You'd win in one area and lose in another. A struggle that we don't want to have anymore. Okay, so the whole mesh approach wanted to take those things into account, and we have, and we've come up with this conceptual mesh approach. So the repeatability, you can save a small thing and then rebuild the big thing as long as you have the same version of RAS. So that's great, and someone else will do the same thing. You want to be able to take a mesh, have your machine, remake it, and get the same thing, as long as they don't change either the conceptual mesh or its parameters. Flexible, the idea that you can put in just a couple of arcs, maybe just one, usually more than one, but you can add as many as you want. But if you think these are things that you're actually making, I mean, how many could you make? 1,000? If you think of how many edges are in a mesh, there's 1 million. Or 2 million on a million-sided mesh. So you're saying, I know what's important, and this area in the middle, just smooth it out in between. Again, light. So when we do backups, we're only saving the conceptual mesh, and these are like 10K, not 10 megabytes. Then I go obedience. So I don't think we have a slide on this, but you might have experienced this a lot when you're dealing with the version 6, that you have two break lines that cross, or they get close to each other, and then you say, I want to enforce this, and it says, hey, I did that, and you're, but I wanted you to leave that one alone. It's like, well, no, I don't do that. I do exactly what you ask, and then the consequences be damned. That was our old approach. So this new approach, where you explicitly state, I want this region, this face is important, and I want it, and you get it. This new approach has kind of brought about a new way of thinking about the problem, inside out or outside in. And if you had asked me when we started this, and you even tried to explain to me that there was going to be two approaches. So the two approaches are, I'm going to take a big region, make one big mesh, fill it with a Cartesian, we're talking a couple clicks in here. I put in a flow here, a boundary condition down there, and I run it. I get it going. This is the way I would have been doing things in version 6. But now that we have the topology approach, it really is easy to define the channel, put in those boundary conditions, and then just run that. Because adding the overbanks is no big deal. You can just add one over here, take a look at that, and then add one, and, oh, maybe I'll do that channel or not. And you can think about how you're going to handle that. You can incrementally build the thing up, and the boundary conditions are all the same. I mean, you just put them at that end and that end, and they get reapplied at compute time. And it would not have occurred to me that I would be heavy in this camp. I really like that. I really like just, let's make the channel first, let's put some boundary conditions on it, let's get some flow going through it. So you might be thinking about the problem this way, and that is the way I thought about it for a long time. But once this became available, I just, one day I noticed that's the way I'm always doing that. Whenever I go to make a mesh, I go put in the channel first, and then I think about how to add the rest of it. Because I want to get water flowing through it first, just to make sure that all is in order. Again, it doesn't really matter. You can do them in any order, but you might think about your procedure to just think about, let's get those quads in the channel right first. Like in this one was just one single channel, it's not a big deal. But if you had a tributary coming in and you were worried about the nuances of how you're going to make those things come together, I would just try to get that done first. There's less cells, it runs faster. Usually just running a channel flow, and I don't start off running the biggest flood flow event ever, right? Let's put a little bit of water in, make sure it's channel full on top and on the bottom. Okay, the different mesh types, we talked about this before. So you got quads, triangles, Cartesian, and holes. And so here's what they look like. So this one's got two quad patches. So there's a quad patch right here, a long quad patch, and then a couple of small quad patches. So we've got these spur dikes right here, and we're trying to control the flow over those spur dikes, and we separate those up as quad patches because we know we want faces there, right? That's why we put in an arc. Cartesian, that looks like, and we've got one Cartesian region here, another one there. A nuance to the new ones, you can have an aspect ratio on them. It's not just the square cells we had before. And then triangles, and triangles are the first or last thing we use to fill in uncomfortable situations. And you'll see that when you're meshing. And then holes, and here's an example. So we've got some maybe oil or water tanks or something where I don't want to put any computational elements in there. So in this mesh, if you put an arc in there and then you would put in some triangles or something, it's not really going to change the compute time because it's not that many cells. But another reason you might want to do this is maybe those are not in the terrain. They might just be flat spots. You don't want water to go there. You certainly don't want water to convey through. So instead of trying to put a vector mod or something in there, you could just say, no, I know water's not going to go through there. Put a hole in my mesh, put triangles around it, and we'll be good to go. Okay, so quads. A lot of nuances with quads. So quads are great. It's my favorite way to fill in the channel by far, and I think everybody should do this all the time. But there are some nuances to it, and we'll look at some examples and some problems with that. The goal of it is that when you say, I have a channel, what you're saying is, if I walked over and we said there's a channel of a river, we would kind of know what we're expecting. That water would be going in a direction that we would expect. So we're going to try to line the cells up to go in that direction. And we want them to go smoothly around curves, and then we'd like them to be longer than they are wide. They don't have to be, but it's usually nice that the differences in velocity and stuff, the computational size of the problem gets better if you make them 3-to-1 or 2-to-1 or something like that. If they're 1-to-1, like if it's around a structure, yeah, you might want to do that. But out in the middle of a long river, no reason not to do something like this. And a lot of reasons to do that. So one of the things that are happening here is we have more cells on this face than we have up there. Okay, so that's kind of a problem. What are you going to do about that? Well, what we do about that is when you want to drop a row, think about this row right here and then that row, you need to have a triangle or something to collapse one cell. And then we try to gradually do that. So you can see the triangles kind of they're read through that way, where we're dropping cells as we go from this number across to up to that number across. There's a couple of parameters that control what happens with that. But again, when you put in the parameters, feel like you're putting them in the cell center, but you're really pushing them to the edges. And he's got some feedback depending on when you're in one region, you're wondering, hey, is this going to be those arcs or those arcs? And the coloring tells you that. Okay, triangles, most flexible, because we have a triangulation algorithm, and it can fill in any region, and it is great in that regard. The downside of triangles is that they're small. They often end up being smaller than you want them to be. The quads, they're easy to make them big. They're in a direction of flow. How do I feel about this? So, well, one, you definitely can do this. I would use the triangles when you don't know the direction of flow. That is one of the things we say about them. It's like, you don't know the direction, triangles are good. And in the overbank, often you don't know, and it might change throughout the event. Okay, so we use triangles to fill in. So we're going to see this in the Cartesian and other things in the transition zones. It's like you ask for something, we try to give you all the big cells you can get, and then we fill in the little areas with triangles. And this is an ongoing process. We're trying to improve that all the time. Okay, so a problem with triangles is that they can get small, and the computation methods, which we've not talked a lot about yet, but the initial computation methods are a combination of implicit and explicit. And what is germane here is if you use an explicit computation approach, they are hard bound on Courant limits. So when you do implicit calculations in RAS and 6x before, you could say, I'm good with a Courant of like 4. That works fine. 3 to 5 or something in there. Explicit methods can't do that at all. It is unconditionally unstable if you get above Courant of 1. Therefore, the smallest cell here, like a small cell that had high velocity, that would rule your time step. And we know that, and we try to accommodate that with spatially varied time steps and stuff, but this is the downside, small cells for triangles. Other than that, it's great. Okay, Cartesian. So this looks very much like what you would have got out of a version 6 mesh. On the edges, it would not look like that in version 6. There wouldn't be that little triangle. It would have just merged that into two 4 or 5-sided elements. We fill in the quads in the middle, and then on the edges, we fill in with triangles. And the same thing happens on internal arcs, is we fill in this quad patch with what you asked for. I wanted them, looks like about 2 or 3 times as long as they are wide. These are 1-to-1. and then I got arc in the middle, and then we fill in with triangles. Then Alex is going to talk about, we have some other processes we run afterwards that try to merge those small triangles. Okay, the empty ones, we saw this a second ago. Water is excluded from, so there are no cells there, there's no water there, and it's a no friction boundary, which might or might not be great, usually doesn't matter, but if these are in the overbank and the water velocities are not very high, it doesn't matter at all. If you're thinking about using one of these for pier where velocities might be high, then you might think about that differently. But just know that. No friction boundary. It still is a boundary, so this idea of trying to fill in with triangles around it still happens. And in this case, it didn't look like it made any really tiny triangle, so that's fine. The icon for it is a null symbol for when you're picking from the little quick pick palette. Okay, so of the meshing options, so there's 3 columns up there. There's a Cartesian, triangle, and quad. And then here's the properties for the regions. And some of them apply. They apply to different things. So for example, rotation angle. Rotation angle only goes into when you're filling in a Cartesian grid. And the cell stretching rate, it affects, for a region, affects Cartesian, triangles, no quads. So there's the palette. It will give you feedback that when you change this element up here, then some of these things will become disabled that matches this. Like there's no point in thinking about curved faces unless you're on a quad patch. And that'll become gray, and you can see that it doesn't apply to you unless you change that top option per region. And these parameters, they are kind of in flux. There's a couple of them. We added a bunch because we did not know we wanted. And now we're looking at each one of them. Do we actually need that one? Is it actually, or was it replaced and did something better come along that could handle that same situation? Okay, so for quads, arc properties are as important as region properties, are more important, because the properties when you put in on quads, they do actually get pushed to arcs. And here's some of the properties for the arcs. They have a target spacing, cell size, or you can do count. And then they got properties. There's a stricter cell spacing one, which we'll talk a little bit more about that and the effects of that. And then the cell density ratio, I guess we'll talk about that too. Okay, so quads are unique. They're the channel element, and I really would encourage you to make your channels with quads, because we're going to do even better advancements on how to make them more channel-like, and taking advantage of knowing that you're saying that's a channel element as opposed to just a general region. When you are on the quick picker, and if you were to click on the quad cell center, the things that are actually going to go into the mesh generation engine are what's on the outside. These things, the arcs that comprises region. And in this case, it looks like we've just got 4, but we could have ever more points on the edges. But this is the thing we've decided is going to be the quad patch. These are going to be the corners. Therefore, we're going to use this information here to propagate here. And you can specify a count here and a count there. They don't have to be the same. When an arc is going around a bend like this, if we had the same number of cells without introducing triangles, what can one say about what happens on the inside versus the outside? Well, the inside arc, this from here to there, is going to be shorter than the outside bend, right? The one that goes on the outside. Okay, what does that mean? Well, that if I ask for 300 here and 300 here, am I going to get either one of those? No, and you don't want to, actually. I really do. This is what I want. I love this. That on the inside of the bend, they're a little bit smaller, and they get bigger on the outside of the bend. That's what it should look like. This is a good mesh. When I said I wanted that, I don't really mean I want that. I mean I want something about that. But I do want faces there, and you do get that. You could go put those arc parameters in by clicking on the arc, or you could go to the region and put a number there, and then when you, depending on which one you have selected, it'll highlight either this pair or the ends, and you'll know which ones are working for you. And this is normally what you expect to look like that. If the quad patch got really, really short, it was wider than it was long, then these things might end up looking reversed. But again, go with the coloring to know what you're going to get, or put in something and then look to see what you got and then realize, oh, it must be backwards, and reverse it. Okay, another nice thing you can do with quads is do this kind of transition where, river's widening up, comes out of a canyon, starts to widen up in the valley, and we get this nice smooth Laplace solution. Has the word Laplace solution come up before in this class? Okay, so a differential equation called Laplace equation is, we use that to define a smooth surface. It's the heat equation, and you can think about, like, if this was an average temperature of 1 here and that was an average temperature of 0 there, then what would a smooth surface look like there? And then we go from one edge of average temperature of 1 here and then 0 there, and we solve the Laplace equation. And the reason I'm telling you about that is some of the parameters in here we actually say, what do you want to use for the Laplace parameter? And you might be thinking, whatever do you mean? It has to do with solving the how we're going to make smooth lines. What is the methodology for coming up with the smooth lines for a quad surface? And we use the Laplace equation. And if you walk by my office, there's a non-zero chance you will hear me say Laplace. And it comes up a lot. But at other people's office, the chance will be less. And again, you can put in count and size to specify either side. Other things about quad. So now we're not talking about this one. We're talking about this space right here. If you say, hey, I want to do a quad patch right there, what is the first thing the quad patch generator does? It tries to find the corners. And if I had 4 arcs, that's no problem. But in this case, I just have 3 arcs. And it's not even clear what you would mean by what you want to do that. So I think if you try to compute that, it'll say, I could not find 4 corners. You need to have at least 4 edges. So you could end up with this, or 4 arcs to make a quad patch. And if you have more, then it tries to determine the best likely candidate. This is another quad patch. And you've said I drew an arc here, and I have an arc here, and maybe I have something else happening over here, so I put another point right there, and another one right there. So now I've got 6 points total. Okay, so what does the program do? It says, well, how many points do I got? I've got 6. I need the top 4. And it goes and looks at the internal angles, and says, this is the sharpest, sharpest, and sharpest, sharpest. These are the most more oblique, so they're not the candidates. Therefore, I'm going to pick the right ones, and I'm going to give you the mesh you wanted. But if you, for whatever reason, you decided, well, I need to have this little weird thing over here, and you put in a little some arcs that look like that. Okay, I don't know why you did that. It might be because this is really large scale, and there's a little inlet or something like that. There could be reasons why you want to do this. But now what does the program do? Is it says, I need to find the corners. Well, that's a pretty small angle, right? So it says, well, that's one of the corners. And then one of these other ones gets dropped. It looks kind of like a bad spider web that you end up with is when it's really trying to make this work, when it chooses those as the corners for quads, and you didn't want that. Okay, what do you do about that? Well, there's a couple things. You could just smooth this out and decide I didn't really want that, or you could just break this up. You could say, well, it doesn't all have to be one quad patch. I could just go from that corner down to like this corner. So these strategies for getting what you want are, I think one that should come up fairly quick is, would it just be really easy just to add another arc across? So in this case, if I really wanted that feature down there, I might add another arc that went from here to here. And then I could get what I wanted. Here's some other pathological examples where we put in some features in here and went around down there, so we got a really distorted, awesome thing there, but not what you want for hydraulics. Then another one, these are all pathological in their own ways, but here's another one. My main channel is right down here, it's the dark area, and then I've got my overbank, and I want to use a quad patch on that too. So I put an arc on the top, and I've got the one falling next to the river, then I've got one on high ground on the other side, another arc right there, I've got 4 arcs total, should be good to go. Will it identify the right corners? It does. Those are the right corners. But transitioning from out to encompass this area, it's not for that. The quad patches is not going to do well with that. If they won't compute it, it will not be good. On the quad patches, and these only apply to quad patches, so there's internal faces when I go around those bends, they're not just straight lines. So when I draw triangles, every edge on the triangle is a straight line. But on the quad patches, we get the curved faces internal. And you can turn that off, but I think we're going to make that default on. If you didn't want that to curve like that, you probably don't want quad patches. Laplace resolution, I mentioned that was how we actually solved the problem. And if you're looking at those curved faces and they're not smooth, then this is the parameter you can change to affect that. Then there's another parameter here, it says quad triangle tolerant. If you leave it at 1, then you said, I wanted 3 cells across, and I want that to be all the way through. I don't want any triangles. Less than 1, you're allowing for some. And when you allow for some, then it says, well, when it gets wider, I'll add some triangles, and then I'm interpreting what you asked for as you want cells this wide. And as it gets wider and wider, I'll start adding extra kind of flow tubes. But in order to do that, I need to add a triangle in the middle of there. If you got that and you wanted this, then that's the parameter to go and tinker with. Here's another example where we're going to increase the number of columns across, where we've got triangle elements to increase the number, and we can see how that looks. If you have it set to 1, then it doesn't do it. So no triangles on the far right when we have that parameter set to 1. When we say cell size, really what we mean is how big is the edge. Artifact of that is, when you say triangles of a certain cell size, and you compare that, if you covered a big area with triangles of a certain cell size, and then you said, hey, what happens if I try Cartesian instead, or quads or something, with the same cell size, you'll get about half the number of elements. And the number of elements are actually the number of unknowns, so it takes longer to compute. So that might mean that if you're going to use triangles, you might use bigger triangles than you would squares, if you're looking at comparable area. Okay, so here's an example with, I think it's the same polygon outline. We took a triangle and said, hey, let's use 200 cell size, and then alternatively, what happens if we filled it with a Cartesian with the same 200 number? What is the cell count? It's about twice as big. The corners make that not a fixed number, but on some level, it really is. Every quad, one of these really does go into 2 triangles. So when you do triangles, you might think about using a larger cell size than what you would use for a Cartesian. Cartesian tools, you can put a cell size, and this is in the primary direction. In the secondary direction, you could put another number there, and then you can also rotate them. Here's the square one. We just rotated this one, and this one, we rotated it and changed the secondary cell size to a smaller number. Now we get cells that are 2 to 1. So that's how you achieve that with a Cartesian. If you put in a Cartesian region, and you ended up with this little row of weird cells on the bottom, you didn't want that, what can you do about that? Well, there's 2 things, or probably a handful of things, but two offhand are, you could make it a quad patch, and then but then all these wouldn't be exactly squares, and if it was really important to you that they were squares, then you would have to use Cartesian. You could use some of our recipe tools we'll talk about later today on how to try to merge some of those, but the edges of Cartesians are going to be filled in with triangles, which then we try to merge into quads. So you end up with something that looks like that. Floating break lines or an arc in the middle of a region, you can do that. Okay, we talked about our topology model where you'd say I've got a start point and an end point, and it does. I think up until this point we've talked about it, you might have been thinking that everything had to be attached to something else, but it doesn't. You can have just a floating arc in the middle of a region. Within an enclosed region, you could put an arc and define a high ground where you want to have the faces line up. And the way we're going to do that is we're going to put whatever you asked for around it. So it looks like we're asking for Cartesian around the whole thing. And then we go in, cut that in there, and then we fill it in with triangles. And then there's the post-processing steps we talked about, or we can try to merge some of those in with more aggressive merging. But this is in default how that happens, is we give you what you asked for in the big area, and then we fill it in with triangles. The cell stretching rate. Okay, so that's one of the other parameters of a region. And what you're saying is here, this is the growth rate. If we want to use a not aggressive growth rate of 0.1, so it says lower stretch rate equals more gradual transition. So we have the cell size out over here, and then we got cells along this arc here from this quad patch. How are we going to grow to go from here to there? And when you have a cell stretching rate of 0.1, it's going to try to grow with every row of cells. It's going to try to make the next row 10% bigger. So it'll take a long time to double before you can achieve the background rate. So in this example, we made it to a cell stretching rate of 0.3. And instead of going further out into this domain, it grew, the cells went from this size to that size over a shorter area. So cell stretching rate will control how big that triangle patch is.